All right, good morning and happy Monday. So I'm planning on doing the LeetCode contest 309 from last Saturday. So doing that virtually. So here we go. All right, open these up. Boom, boom, boom. Check distance between same letters. They occur twice. Distance appears at 0 and 2. So satisfies distance. So true. S is a well-spaced string. This one is not well-spaced. A appears indices 0 and 1. So there's 0 letters between them. There's 1, 2, 3 letters between that one and that one. Okay. So subtract 1 since it's not inclusive from I to J. The zeros. Ith letter does not appear in S, then distance of I can be ignored. Distance of length 26. Okay, so it's A, B, C, D. Okay, that makes sense. All right, so let's do this in Python 3 since it's the most simple. K away from each other. String, and then, oh, distance is an array. How about string and array? Sounds good. And will be our map. All right, and then so for each character in the string, so let's do I, enumerate, so know where the character is at. If C and M, then the last distance yes, the last distance will be in the map as J. Distance equals M sub C, I minus M sub C minus 1, minus 1 for I, J, non-inclusive. Okay, and then the array for that character is at the ordinal value, or equals lambda C. Oh, or it's actually right. So if A sub ordinal value of C minus ordinal value of A is not equal to the distance, return false. Otherwise, return true. And then if C is not an M, the name sub C equals I. Okay, something like that. True for the first one, false for the second one. Sounds good. Yay. Number of ways to reach a position after exactly K steps. So how long did that take? Hold on. This took 5 minutes. I see in about 5 minutes. Okay, so Should I go on to the next question, or should I just do this in all the other languages? I might as well just do this on all the other languages, whatever. Right, so use a map, keep track of the ith index, and then compare it to the array of indices that's expected. All right, so you could clean this up a little bit if you wanted to. It doesn't have to be perfect. It's good enough, whatever. All right, so let's do this. A few solutions. Use a map m to store scene characters. Store the index of each character C of the input string S and to compare the distance against the input array A of expected distances. That was good. Kotlin. JavaScript. Python 3. Rust. C++. Okay. Doesn't have to be perfect. Good enough, right? That's cool. Stick that there. Do C++ next. How about? Okay. Expected distances and using map. Map. Character index value. And there we go. So for auto 0, just that. It's capital just for consistency. Minus. C equals S of I. If m dot find C, equal m dot n, then have it. Otherwise, if we don't have it in the map, we'll add it there. Distance equals I minus m sub c minus 1. So minus 1 for I to j non-inclusive. If a sub c minus a is not equal to distance, we return false. Otherwise, we return true at the end. Okay. Looks good. Looks good. Oh, hold on. Bam. Okay. Let's do JavaScript. SA. M is our new map. Or equal 0 is less than string is I. Character is s sub I. And if m dot has the character, otherwise we'll add index onto the map. Return true there. Distance is m dot get sub c, and I minus that minus 1. That's 1 for I, j non-inclusive. If, let's see, let's do the ordinal. Ord is c dot char code at 0 minus, let's just do it. Yeah, whatever, it's fine, right? A dot char code 0 ordinal c, so a sub ordinal c. And let's do this. It's fine, right? So minus the ordinal value of a. It's not equal to distance. Return false there. Okay. Looks good. Looks good. Good enough. Okay, it doesn't have to be perfect. Move on. Let's go. S A M is our mutable map of characters to integer index of that character for IC in S dot with index. If the map contains C, character, otherwise M sub C with I, distance equals M sub C, I minus that, minus one for I to J non-inclusive. If the array index is not equal to distance, and return false here. And then ASCII ordinal value for this is .2 int c dot 2 int minus a dot 2 int. Return true at the end here. Okay. Looks good. Looks good. It's cool. All right, let's do Rust last to save the best for last here. All right. Vector by 32s. Boom. Okay, coffee break. All right. True at the end, and then mutable map equals hash map. STD collections hash map for to index S. It's a vector of characters. Hold on. Chars collect vector characters. Or ICN. Oh, actually, I don't need this. I can just do a linear scan, right? S dot enumerate, S dot chars dot enumerate. I think it has to be like that to destructure it. Okay, so if m dot contains p, that, otherwise m dot insert ci distance equals I minus m dot get c dot unwrap minus one for I to j non-inclusive. If a sub does not equal to distance, return false there. So this needs to be the ASCII ordinal value of that character. C as U8 minus A as U8. I think that works, something like that. Big money, no whammies. Oh, oops. Gotta borrow that guy. Slices, indices of U size or ranges of U size cannot be indexed by U8. U size. Oof. No implementation for I-32 equals U size. Distance is a U size. Oops. As I-32. Okay. Big money, no whammies. Okay, that's good. Yay. Okay. And that's cool. Let's move on. All right. Use mapm to store the index of each character C of the input string S to compare the distance against the input array A of expected distances. Okay, sounds good. Okay, and we have 1 hour, 15 minutes left. Out. Okay. 1 hour, 15 minutes remaining in the contest. So it's cool. Okay. Number of ways you can reach a position. So we get case steps. Negative integers is cool. 1, 2, 3, and then back to 2. Okay, so we can go left or right. Right, so this seems to be a recursive algorithm with k minus 1 steps after each additional step. So we can keep track of that in a memo. Recursively solve this one. That's the game plan, right? Game plan. It's going to be begin, it's going to be end, and okay, it'll be there. Go, go. Okay, so current I position is where we start at. I equals begin. Step equals K. If not K, return 1 if that's int I equals end. Right, we have no, oops, not step. No more steps remaining. Are we at the last position? Otherwise, go left one and right one. So left equals go, I minus 1, step minus 1. Right equals go, I plus 1, step minus 1. Turn this R. Okay, so it's 3 and 0. Looks good. So you just have to memorize it maybe for TLEs. I don't know. Let's see. Big money, no whammies. Actually, whammies are good as long as we consider them in the right way. That is, failure is an integral part of the path towards success, right? Failure is part of the journey. So anyhow, yeah, and it's as simple as this, right? Cache. Oops. This there. So just do the memoization. That's cool. Big money, no arms. I expect this to not TLE, right? Oh, dang. Uh-oh. Oh, the mod. I forgot the mod. I always forget this mod. Oops. Okay. modulus 29 plus 7. Okie dokie. This guy, we expect 934, 81, 896. Okay, cool. Looks good. Big money, no whammies. Big money and whammies. Okay, cool. So that's that. And I wonder, do I want to try to do bottom up? This is top down, so what would bottom up look like? Yeah, two-dimensional array of steps. I goes negative. Yeah, bottom up would be a huge pain. Yeah, whatever. Let's just do this for now. It's good enough. A few solutions. Oh, cool. This dude did do bottom up. That's awesome. Okay. Wonder if I want to try begin and then oh actually, you know what? Yeah. So just use a map. Store this. Okay, here this is top down. Top down DP memo. Use the memoization to avoid TLE, overlapping subproblems. Let's see. I don't want to spend too much time on this, but it should be worth a shot. Bottom up. Actually turning it upside down. So what happens at each recursive well, step goes down by 1. So we're going to have to need case steps for our array of minimizations of states. So let map have the key, right? So since I can be negative, we can use a map instead of an array. Going left. All right, okay. So the key is equal to index and then steps. Let's do this hash. Oops. This key is lambda. Lambda. Ith step. How many steps do we have left? I is equals to the end. Step in range K. So those are our steps. The recursive stack will unwind at 0. Starting at 0, we can build upon it. M sub key end 0 equals 1 is our base case. Similarly, here's our base case. 0 steps left, and we're at the end index. And then we can build upon that. One to K. Inclusive. and then accumulate the sum of all the values of the map. So upon one, we'll add on the other states modulus 29 plus 7. All right, so we can go to the left or we can go to the right. Right? I minus 1 step minus 1. Go to the left. It would be step plus 1. How many ways for to keep it super simple? Oh, so we start at the end and then go back to beginning, right? So we want to actually, now we want to return m sub key begin, beginning with k steps, right? Ending with 0 steps, beginning with k steps, plus 1, like that one. All the states in the map. Okay, so for each state in the map, we can add on to it I. These are steps, but I don't think I need those. I step and into items. From that previous state, as the recursive step unwinds, we can build upon that state I minus 1, I plus 1 with an additional step. Right, we have some value for that. M items. Oh, hold on. It has a key and a value. So I'd have to destructure the key. Let's see, let's call this an encode and decode. How about encode, and then decode. Key dot split. And then we'll map that into an integer. Destructure that. Okay, so key step. actually it's key and then count, right? Key count, and then the ith step is decoding the key. Step plus one, I minus one and plus one, right? So L equals number of ways. So is it the number of ways there, right? Is it, okay, so the current ith step is the left plus the right. Built upon the previous steps. Not sure if this is the right recurrence relation note for each. Yeah, k step is decremented by one as the recursion goes deeper. So k is incremented by one in the opposite way. It's the ith step, and then I guess L can equal sub. It's got a counter. So we use the default. Actually, we'll just call it default tick. It's fine, right? Default tick int encode I minus one step plus one. This to the left. This guy is to the right. Current I step equals those ones, right? M sub key plus equals M sub key plus L plus R modulus 29 7. Right, add on to yourself the left and the right. Does that work? Maybe. I don't know. Oh, X. There is no X. Int S. Dictionary change size during iteration. Oh crap. Okay. That's not gonna work. Oh. Ah, I see. Okay, we'll need a next map then, I guess. Previous. Current equals previous. Her equals default. Dict. Her equals cur. Current is based on previous plus previous. Something like that. M previous items. Dictionary change size during iteration. Really? Previous is changing? Previous. Oh crap. Okay. Uh okay. All right. No defaults then, because I'm pretty sure that's causing a problem. Okay. If that guy is in pre else 0. If that guy is in previous 0. Previous key is the count. Oops, no. Previous keys. I step upon which we build left and right. Step +1. Current based upon previous key error 1 3 pre does not exist. If in pre else 0. Uh-oh. Okay, well, that did not work. All right, yeah, bottom up is something I made a big old mess out of. Oops, okay, so I made a big mess. Bottom up. Alrighty, yeah, that didn't work. Let's just do this. Print pre print cur empty. 1, 2, and 3 is the easiest one, right? 1, 2, 3. Let's see what's going on. Well, that doesn't look right at all. Start, end, and K. Start, end. So that's end and 0. Hold on. Do this count items. So the current, this is current, right? This is current. Equals itself plus that count, right? If this guy's in current 0, the count plus that odd 29, 7. Just mod. Hey, hold on, I can mod it later here. Should be okay, I think. So the current is the previous count plus, let's do this. I plus 1 plus 1. So that's current. Okay, yeah, so I do want the modules. Oops. Modules mod. Modules mod. Okay, so building each current step based on the previous count step. Key is decoded there. Previous based on current. Previous is there. Okay. That looks good, right? Okay, cool. 3 is good. 0 is cool. Okay. So then let's try these ones. Oops. Uh-oh. It's taking, oh, it's just printing a lot. Okay. Maybe it's cool. Let's get rid of these print statements and then see what happens. Oops. Print pre. Okay. Taking a while, but maybe it'll be okay. I don't know. Oh, oh, okay. So Tia lead. But still, this is a pretty good bottom-up solution, I think. Yeah. Okay, so how to make it a little bit faster? Encoding and decoding. Okay, this works, but TLEs. What's the previous based on the current? So if I goes negative, would you handle that as a 2D array? Map of a map, maybe? I step back. All right, that's a big mess. But this is correct. It's a correct solution. Just slow. Based upon previous. Key times. Yeah, so yeah, I didn't want to spend too much time on this one. I got 44 minutes left. I'm certain we can turn it upside down without a TLA. All right, if we build in from that one up. All right, well, let's just do this for now. 3 solutions. Do the bottom up next. For now, let's just do this, right? And solutions, JavaScript, solutions. Okay, that's cool. Now let's just do this top down here real quick, and then work on the bottom up a little bit more, maybe afterwards. Okay, so action go. I step. Step. Then, oops. Turn. In. Oops. End. One is our function. And an integer. Now let's go I minus 1, step plus 1. Oops, step minus 1. Let's go I minus 1, step minus 1. Turn L plus R, which was 9, 7. Okay, so that should work, but TLE without the memo. Oh, oh. Again with case steps. Uh-oh, 0 and 0. I equals end. What happened? I equals end. There's no steps left. Ooh, I plus 1. Oops. I plus 1 to go right. I minus 1 to go left. Okay, that's cool. That should TLE. Add a memo. And it's okay. hash code is step. Okay. And here's a if equals, oops, and I should fill out the next step. And oops. If we don't have it, then we'll compute it once and remember it for future lookups. Okay, that looks good. And then this guy should not TLE. AP is cool. Oh, this one's still top-down TLAs. I need bottom up. All right, let's see what happens in Kotlin and JavaScript. I have a feeling they will be accepted as well. And poor C++ has a hard time because it's so fast. You just have to let go of that ith step. We begin at begin, kth step. We have 0 steps left. Return I equals begin. Oops, end is our target. Left, let's go -1, step -1. R is going to the right, +1. And R. Modulus number 1E9 7. Okay, so that should work without that. It's cool. And then with the memo, be accepted, I believe. Hash equals the ith step. I step equals hash of the ith step. And if the map does not have the key, we'll compute it once, store it for future lookups. Okay, and then stick that there. Oh, nice. Hash equals that equals that. Okay. What is this? It's not a value. Oh. Oops. I mean to grab that. See 413. Okay, looks good. Looks good. Okay, the online judge is lenient to everything besides C++ and perhaps Rust. Let's see. Okay, so Kotlin is next. And okay. Function go is integer equals begin. Step is an integer equals k. Turn integer at the end. If step is equal to 0, then we'll return. If I is equal to end 1, y 0, and then left equals go I-1, step -1, right equals go -1, step -1, turn L plus modulus 1e9 7. Okay. And that should be fine for these. 3 and 0. Okay, and then if we want this one to pass, we have to add the minimization to avoid TLE. Mutable map of string. Sure, I think we can use a pair, but I'm not sure offhand. Okay, so that's fine. Hash, oops, hash. As an integer, step is an integer, and we'll return the ith step as the key. Hash, oops, if index contains key, get it once for future lookups. Turn it at the end here. Okay, something like that. Looks good. It's cool. Okay. I had a lot of coffee, so I gotta pee real quick. I get my music back on. Okay, so yeah, you gotta turn these things upside down. Let's see. Build the oops, the current. Use DP to build the current count. For I step. Based upon the previous count per adjacent I minus 1. And I plus 1. I left and right correspondingly. Something like that. We'll come back to that because that's super cool to turn it upside down. That is a bummer that this TLE, based on the previous items, we create the current. Actually, current, we can do this a default deck. Maybe that'll be fast enough. I don't know. Current plus itself modulus mod. Current plus itself modulus mod. Maybe that's fast enough. Previous via default dictionary of integers. Current is based on previous. Okay. And then what did I TLE on? This guy. Oh, that one's cool. Okay, so I TLE'd on this guy. So maybe it's close. Here, I think it comes up with an answer, right? This doesn't result in TLE. 0. I wonder if we can remove some branches to speed this up. This is a pretty decent solution, though. Building the current based on the previous, and then, well, yeah, it's kind of a crapshoot. So the question here is how to speed this up. Okay, we've got 30 minutes left, so we'll move on. I don't know. Let's come back to this later. Try to upsolve. Okay, along this nice subarray, here given an array of nums, because these are positive integers. Because subarray nums nice, it's bitwise, and every pair of elements that are in different positions in the subarray is equal to 0. Function the length of the longest nice subarray. A subarray is contiguous. Okay. Longest nice subarray. 3848. Bitwise, and this looks like maybe Duquesne's algorithm. Right, so this one contains algorithm of best ending here for each index. That is, we can, for each item, we can pin it onto the ongoing subarray. Case 1. Case 2. Create a new subarray with length 1 at I, right? Let's see. Okay. So this is the game plan, and this is what we'll return for mask equals 0. Mask will be our bit mask for x in A. if not x and mask, then we can append it on there. Mask or equals x. And then the length is +1. Count 0. Count less equals 1. Best equals max. Best count. Otherwise, mask equals x and the count equals 1. Something like that. Okay, we got 3 and 1 are the answers. Oh, else. My L key is messed up. I hit that one extra hard. Okay, that was good. Uh-oh. It's 7, but I expect 8. 7, but I expect 8. What's going on? These are big old numbers. 29 should be fine. I would say not enough. Not adding enough. Hmm. That's strange. Print the binary format of these things, I guess. Binary value of x. Let's debug it, I suppose. What's am I gonna do? I don't know. Oof. Oh man. I'll pad it to 32. Pad left. String left pad. Let's see. Python 3 left pad. I'm gonna pad it left with zeros. Where's the API? Zfill. Ljust. That's what I want, right? Ljust. Okay. Left justification, I think. Ljust. Oops. And representation of x dot Ljust 0 to 32. So they align, right? Uh-oh. Binary representation of x. Hold on. Say x is equal to this first value. How about x equals that guy? Binary value of x is this guy. And we want 2 onwards. That's what we want to left justify. Integer. What? Oh. It's backwards. 2 and 0. Okay, so we're saying that 8 of these things do not overlap. Mm. Let's do this. 1, 2, 3, 4, 5. How about something I can actually read? Okay, this is the wrong way, actually. I want to adjust it. Adjust, right? Okay, that looks right. Okay. Now, which 7 do not overlap? These ones certainly overlap. 1, 2, 3, 4, 5, 6, 7, 8. These ones are okay. Yeah, so these 8 are cool. And then these ones overlap. Okay, so I'm pinning this one onto that one. Pasting in here is the best of pasting in here plus this one or starting a new one there. I'm not considering both cases. Right, okay. So the game plan seems correct. The implementation is flawed. Yeah, there's a software defect, right? This is a candidate, and then this is also a candidate. Candidate equals 0. Previous best and net previous I plus 1 or current best. The current I. Ith mask to keep track of it. Current and previous, okay. Ith mask. And then that index I. Starting from 1 onwards. There's always 1, right? So 1, there's always 1. Best is at least 1. Mask equals a sub 0. Or that state, right? The previous ith state. So use m to keep track of that. M ith mask. M sub 0 mask is 1. M sub ith mask is 1. Okay, so case one is appending it onto the previous. So previous will be just to keep track of the mask and the mask and the value. Mask and the value. So previous mask m sub I minus 1. M sub I equals that mask in 1. Previous is this guy extending here. It's actually, yeah, the best ending here is either 1 or with that guy. Previous is a single. I structure this in a way that we can build current upon previous optimally. This guy builds upon that guy. Let me start a new one here, though. Without that one. With the previous and without the previous is what we need. With and without, right? Include and exclude. Include previous and exclude previous. There are two cases. Include and exclude. Include exclude. Include equals m sub I minus 1. Exclude equals 0, m sub I minus 1 sub 1. With it and without it. With it and without it. Previous include and previous exclude. Current include. Oh man, okay, so hold on. Keep it super simple. Don't confuse myself. Okay, how much do I got? I got 10 minutes. I'm pretty sure I can do this in 10 minutes. Include and exclude. Okay, so include or exclude this previous one. If we include it, we can add one onto it. If we exclude it, it's just this. And then on top of that, we can do the include or exclude. Include and exclude. Current include and current exclude. Based on the previous include and exclude. It's going to be previous and then current include goes in. Best of including it on exclusion or exclusion. Yeah, this is tricky, but I'm pretty sure I can get it. Long as no separate, it's a flavor of Gadane's algorithm invested in here. Right, so we have to keep track of the bit mask and the value to see if we can include it on top of the previous. Previous include mask. Include value count pre-exclude mask pre-exclude count good current include equals maximum of including X on either of those. And I don't know. There's got to be a cleaner, better way to doing that. Okay, we got 5 minutes left. So you can append that onto this as 1, 2, 3, 4, 5, 6. Challenge here is this one go with this one or this one go with that one? So include would include that one. Include this and time put exclude of that. Hmm. Actually, if you exclude the previous, it's zero, right? Hold on, yeah. So I'm gonna keep it super simple. Keep it super simple. Right, so just keep track of including it here. And exclude is implicit, isn't it? You just don't take it. Exclude the previous, then would be m sub I equals, right, we exclude the previous. We just say, hey, this is a brand new one without the previous. Not the previous. I do still need to keep track of it though, even though it's not going to be the best, it's going to be one. This one's tricky. It's doable, but it's tricky. 2 minutes. Yeah, so I do need to keep track of the previous two states for ith index, right? Right. Include. It's not going to be optimal here to exclude it because we have 1, 2, 3, 4, 5, 6. It would be the sixth one that's appended onto. Oh, wait, it doesn't go there. Okay, well, anyhow, it would be appended onto this one. 2 is always better than 1, but I want to keep track of that 1 has a potential to build on next. To keep track of the optimal solution as well as the potential alternative. I can build on both. Excluding previous. Okay, well, this is a good one to come back to. 35 seconds. I don't think I'm going to solve it in 35 seconds. This one's cool, though. I like this. This is dynamic programming used in the past to formulate the future. So we'll come back to it for sure. Catch you next time.